Have you ever wondered why some welded metals become stronger while others become brittle? That's because welding doesn't just connect metal together, it also changes their internal structure due to extreme heat. In industries like construction and manufacturing, welding is very important because it helps create strong metal structures and components. But after welding, the way the metal cools down can greatly affect its hardness, strength, and overall quality. That's why studying welded steel is important to ensure safety and performance. To better understand these changes, the welded sample were examined using microstructural analysis and hardness testing. Microstructural examinations allows us to look inside the metal using a microscope. This helps identify grain growth, phase transformations, and changes in the heat-affected zone or HAZ. Hardness testing was also performed across the weld area to measure how strong or hard different parts of the metal became after welding. This study compared three cooling treatments: air cooling, water quenching, and tempering. Each method affects the metal differently depending on how fast or slow the cooling process is.
This methodology involved welding steel samples and applying different cooling treatments to study their effect on hardness and microstructure. After preparation and etching, microscopic examination and microhardness testing were performed for data analysis. This diagram shows the methodology used in analyzing the microstructure and hardness of welded steel samples under different heat treatments such as air cooling, water quenching, and tempering. After welding and sample preparation, microscopy and microhardness testing were conducted to evaluate the effects of welding and cooling conditions on the material properties.
For the discussion of results, we have sample 1A, air-cooled, showed a gradual decrease in hardness from the weld zone to the base metal, indicating a uniform heat-affected zone and consistent cooling behavior. The weld area exhibited higher hardness due to thermal exposure, while the regions farther away become softer because of reduced heat influence. For the sample 1B, air-cooled, exhibited a high initial hardness near the weld followed by a sharp decrease, suggesting a steeper thermal gradient and faster microstructural transition. The rapid hardness drop indicates stronger thermal effects near the weld compared to sample 1A. For the sample 2A, water quench showed a steady reduction in hardness with increasing distance from the weld. Reflecting uniform cooling and heat dissipation, the water quenching treatment increased hardness near the weld due to the formation of harder microstructure such as bainite or martensite. For the sample 2B, water quench, recorded the highest hardness among all samples because rapid quenching formed very hard and brittle microstructures near the weld zone. Its regular hardness trend suggests uneven cooling and complex microstructural changes farther from the weld. For the sample 3A, tempered, displayed lower hardness values compared to the quench samples because tempering reduced brittleness and relieved internal stresses. The gradual decrease in hardness indicates a more balanced and stable microstructure throughout the heat-affected zone. For the sample 3B, tempered, showed a smooth and consistent decrease in hardness with distance, indicating controlled thermal behavior after tempering. Although tempered, it maintained relatively high hardness, suggesting a good balance between strength and ductility.
So for data analysis, we have sample 1A, which showed a sharp decrease in hardness. Sample 1B, which showed a gradual decrease in hardness. For sample 2A, which shows a linear decrease of hardness. For sample 2B, this is the highest hardness we recorded. For sample 3A, this is the lowest hardness we recorded. For 3B, this is a linear decrease in hardness. So for table 1, we have a p-value of 0.0152, which has which is less than the alpha level of 0.05. Therefore, we reject the null hypothesis, indicating that the measurement location has a significant effect on hardness. So for table 2, we have a p-value of 0.1057, which exceeds the 0.05 threshold. Therefore, we fail to reject the null hypothesis, concluding that the differences in hardness across three measurements are not significant. For table 3, we have a p-value of 0.0790, which is above the significant levels of 0.05. Therefore, we fail to reject the null hypothesis, indicating there is no significant difference in hardness values across the measurement locations. For table 4, we have a p-value of 0.0097, which is below the alpha level of 0.05. We reject the null hypothesis, and then we have a omega square value of 0.691, which indicates a large effect size, confirming that the location or measurement location influences the hardness of the sample. For table 5, we have a p-value of 0.2213, which exceeds the 0.05 level. Therefore, we fail to reject the null hypotheses, concluding that the location measurement did not produce significant differences in hardness values. For table 6, we have a p-value of 0.00058, that is well below 0.05 threshold. Therefore, we reject the null hypotheses. But with an omega square value of 0.876, this sample demonstrates the strongest effect size among all groups, indicating that distance from the weld point has a highly significant influence on hardness.
For the conclusion, this study demonstrated that post-weld thermal treatments plays a critical role in determining both the microstructure and mechanical properties of welded steel samples. Across all three treatments conditions, which is air cooling, water quenching, and tempering, we observed three consistent findings. First, water quenching produced the most significant microstructural changes. Sample 2B recorded the highest initial hardness at approximately 158 HV at the weld point, owing to the rapid cooling rate that promotes the formation of martensite and articular ferrite, faces that are hard but brittle. Second, tempering after quenching applied at 500 degrees Celsius for 20 minutes. Reduced peak hardness to around 110 HV. While this means a loss in maximum strength, it relieves residual stresses and transforms some of the brittle martensite into more stable phases, improving toughness and ductility, making the material more practical for real-world use. Third, all samples consistently showed a decrease in hardness with increasing distance from the weld, which is a direct result of grain growth, phase transformations, and recovery effects in the heat-affected zone. Overall, our findings confirm that choice of cooling treatment after welding is the primary factor controlling the final mechanical and microstructural properties of welded steel joints.